Swayam Prabha. Digital India. Educated India.
Welcome to the 9th lecture of the lecture series on tutorials on design of transmission elements. In the previous classes, we studied about the problems related to different gears, and those gears were spur gear, helical gear, bevel gear, worm and worm gear. And in the previous class, we studied about the sliding contact bearing. Now, in this lecture, we are going to take another type of bearing, which is the rolling element bearing. In this rolling element bearing, the shaft is separated to the bearing with the help of rolling elements. In the case of sliding contact bearing, there was a lubricant, and the contact was a sliding contact. So, let us start with a brief introduction of rolling element bearing, and thereafter we will take few problems related to selection design of rolling element bearing. Actually, the design of rolling element bearing is the selection design of rolling element bearings, in which based on our requirement, we select a suitable rolling element bearing from the manufacturer's catalog. In a rolling element bearings, the contact between the bearing elements is rolling instead of sliding as found in the journal bearing. So, in the rolling element bearing, this one is the inner race of the bearing, and inside the inner race will be the shaft. Sometimes it is not in this way, depending on whether the inner race has to rotate or the outer race has to rotate. But in this figure, the shaft is in this one. This is the shaft or the journal, and it is separated to the bearing by the rolling elements. And this rolling element may be a ball, it may be a roller, it may be a pin or the needle, it may be a tapered roller like that, depending on the requirement, depending on the type of load which we want to support. The shaft is supported on rollers or balls or pins. A bearing of this type has a very small friction, the reason being that the friction due to rolling of surfaces over each other is considerably less than the sliding friction as shown in this figure. In the case of sliding, the two surfaces are direct in contact, and when we apply a force to slide the upper weight, there will be appreciable amount of friction here. Now, if a lubricant is placed in this place, then the amount of friction will be reduced, but there will be appreciable friction. Now, if these two surfaces are separated by rollers, then the amount of friction will be considerably reduced, because now the contact between this and this will be the point type of contact instead of surface contact. This principle is used in the rolling element bearing, where the bearing has the inner race and the outer race, and inside the journal will be. And the journal is separated to the bearing by the rolling elements, which may be a roller, it may be a ball, or may be pin, or may be tapered roller. A bearing is to support only axial load, then it is called the thrust bearing. This is a combination where both radial load acts along the axis of rotation of the journal or the shaft, and the axial load acts in the direction of the axis of rotation. There may be a case where only the radial force will be there, only radial force, and therefore, there will be only Fr. And when there is only axial load, then it is Fa. Now, depending on what amount of axial load and radial load is there, we have to select different type of bearings. This table illustrates about that. In the first column is the different type of rolling element bearings, and in the second column the amount of radial load carrying capacity is given, and in the third column is the thrust load capacity and the direction in which the load can be applied. For example, for the case of single row deep groove ball bearing, two directional load can be applied, but the amount of radial load, if it is Fr, then the amount of thrust load should be 0.7 of the Fr. It means if the thrust load is 0.7 times Fr maximum, then we can use this deep groove ball bearing. In the filler notch, the filler notch bearing will be selected when the radial load is 1.2 to 1.4 the radial load of the deep groove ball bearing or the radial load of a radial bearing, and the thrust capacity is 0.2 of the Fr. Similarly, the angular contact will be selected when this will be the Fr and this will be the thrust load. This is the terminology which are used in the rolling element bearing. A typical rolling element bearing is shown here. In this, the load can be applied both in the radial direction and in the axial direction due to this type of race. It can support a load in this way, and so it will have a component in the radial direction and in the axial direction. So, it can support both type of load. Now, in this figure, this one, the inner diameter of the inner race is called the bore diameter. Bore diameter D, and capital D, this one, outside diameter of the outer race will be the outer diameter capital D. B is the bearing width, this was the bearing width. Then H is the height. In the case of thrust bearing, this is a thrust bearing in which the load can be carried only in the direction of axial. So, the height is given by this H. Then R is the chamfer, this chamfering is there at the edges like this, you see, chamfering is there here also. And the alpha is the contact angle. This is for a particular case. If a pure radial bearing will be there, in that case this alpha will be 0. In this figure, different ball bearings are shown. This one is the thrust bearing and the radial bearings. Here the rolling element is the roller. See, here it is a ball. Now, standard dimensions according to Anti-Friction Bearing Manufacturers Association AFBMA, a bearing is denoted by two digits. The first digit represents the width series, which is the ratio of width, means this B, to the bearing section height. 8 standard width series are there, which are denoted by 8, 0, 1, 2, 3, 4, 5, 6, where successive number indicates the increasing value of the width series. Okay, this width series. So, if you are moving in this way, the width series is increasing. That means the ratio of width to section height is increasing. The second digit represents the diameter series. It denotes the outside diameter of the bearing. That means this capital D. 7 standard diameter series 7, 8, 9, 0, 1, 2, 3 and 4 were established, where 7 represents the smallest outside diameter. It means if 7 is there in the nomenclature of the bearing, then its outside diameter will be the smallest. These are shown here. The width series is represented in this figure as 0, 1, 2, 3, and you see when you are moving from 0 to 1, 2, 3, then how the width is increasing. It is the width series actually, but the width will increase. This is the 0, this is the width, and the diameter series, you see with the increase, when you are moving in this way, the outside diameter is increasing. This one is the axis of rotation. This is axis of rotation, like this one. So, only half part of the bearing is shown in this figure. Now, let's take any one example. Let this 0, 0. 0, 0 means the width series is 0 and the diameter series is 0. Then this part of the bearing, will look like this. Now, when we are making it 1, 0, that means now width series is 1, but the diameter series is same, and so the outside diameter will remain same, but the width is increasing, and so you see the shape is now this one. This shape. See the difference between 0, 0 bearing and the 1, 0 bearing. Similarly, when it is 1, 2, then the outside diameter has increased. Outside diameter is 2 now. This is the diameter series, this is the width series. Width series is 1 and the diameter series is 2. So, diameter has increased and the width series has become this one. So, this shape of the bearing is now this one. So, with the change in your first two digits of the bearing nomenclature, the shape of the bearing will change. Now, see for example, the width series is 3 and the diameter series is 0. When the diameter series is 0, then the diameter will remain same, but now you see the width. See the difference between these all 0, 0, 1, 0, 2, 0 and 3, 0. In all the cases, diameter series is 0, 0, 0 and 0. So, the same outside diameter will be there. But as the width series is changing from 0 to 1 to 2 to 3, the width is increasing. This width B will be increasing. To illustrate the Anti-Friction Bearing Manufacturers Association procedure, suppose a bearing is designated as 20 BC03. So, this 20 represents the bore of the bearing. It means this one. This small d is 20 and BC represents the deep groove ball bearing. Deep groove ball bearing, and 03 number, in that the first one is the width series and second one is the diameter series, means 03. So, we will have a 03, it means this one. It means outside diameter will be represented by this one and the width this one. This will be the shape of this part of the bearing. Okay. Now, the bearing manufacturer SKF nomenclates its bearing slightly different than the Anti-Friction Bearing Manufacturers Association's method. So, in the SKF, the last 2 digit represents the code for the bore. That means, if the nomenclature of the SKF bearing is SKF 6308, then the last 2 digit, this 03, represents the bore. Bore means small d of the bearing. The small d is this one. This is the small d. Well, so the digits 0, 0, 0, 1, 0, 2, 03 represent 10, 12, 15, 17 mm bore respectively. This is written here. If it is 0, 0, 01, 02, 03, then the bore will be 10 mm, 12 mm, 15 mm and 17 mm. Now, if it is more than 3, then the bore will be that number multiplied by 5. Okay. So, the digit starting from 04 represents 1/5 of the bore in millimeters. The SKF bearing catalog has denoted 03, 02, 03 series as 62 and 63. So, if the width series is 0, diameter series is 2, then the SKF represent it as 62. If it is 03 width series and diameter series as per Anti-Friction Bearing Manufacturers Association nomenclature, then SKF represent it as 63. So, it is written here, this 6, the first digit represents the type of bearing. That means, if 6 is there, then it is deep groove ball bearing. If in place of 6, 3 is there, then it is taper roller bearing. In place of 6, if 2 is there, then spherical roller bearing. And similarly for other bearings, type of bearings, the digits are there. This second digit represents the type of series. 1, that is 100 series extra light, 200 series light, 3, that is 300 series medium, 4, that is 400 series heavy, 5, that is 500 series extra heavy. Now, to illustrate this, let us take the SKF 6304. So, the first two digits 6 3 represents, this 6 represents deep groove ball bearing, 6 means deep groove ball bearing, and this 3 0 3 actually this is actually 6 3 means 0 3 width and diameter series. So, diameter series is 3 and the width series is 0, and this 0 4 multiplied by 5 will be the bore. That means the bore is 20 mm. For 6304, for 6308, the bore will be 08 multiplied by 5, that means 40 mm. These are SKF way of nomenclature. Now, selection of bearing type. The type of bearing in a particular application depends upon the requirement of the application, the characteristic of the different type of bearings. For low and medium radial bearing, we go for the ball bearing. For heavy loads and large shaft diameter, we go for the roller bearings. For deep groove ball bearing, angular contact bearing and spherical roller bearings, in applications where the load acting on the bearing consists of two components, that means radial and thrust load both. Self-aligning ball bearing and spherical roller bearings are used in applications where a misalignment between the axes of the shaft and housing is likely to exist. That means a misalignment will be there, like that. The thrust ball bearing for medium thrust loads, for heavy thrust loads, cylindrical roller thrust bearings are recommended. Double acting thrust bearings can carry the thrust load in either direction. For high speed applications, deep groove ball bearing, angular contact bearings and cylindrical roller bearings are recommended. High rigidity, double row cylindrical roller bearings or taper roller bearings, for example, machine tool spindles, are selected. Low noise applications. In low noise applications, deep groove ball bearing, for example, household appliances are used. Now, the selection methodology. Determine the value of the radial load factor X and the axial load factor Y. We will study what is this X and Y. The values of these factors depend upon two ratios, FA, the axial load on the bearing, and the radial load on the bearing, this ratio, and FA upon C0, where C0 is the static load capacity of a particular bearing. Then compute the equivalent dynamic load FE from this equation, VXFR plus YFA. Decide the expected life of the bearing, convert the expected life in hours into millions of revolutions, calculate the dynamic load capacity from the load life equation, check whether the selected bearing has a required dynamic load capacity or not. If yes, the selected bearing is suitable for this application. If no, then we will go for another bearing. So, let us take one example. A shaft is rotating at 1440 rpm, is supported by two bearings. The forces acting on each bearing are 600 Newton radial. So, on this bearing, the radial load which is acting Fr is 6000 Newton and 3500 Newton axial. So, the axial force which is acting on the shaft is 3500 Newton, not on the shaft, but on each of the bearing which is supporting the shaft. If the shaft diameter is 40 mm, it means it is giving the bore of the bearing. Shaft diameter is 40, it means bore of our bearing should be 40 mm. The expected life of the bearing is 500 hours. Select a suitable bearing. Now, first of all, what we will do is, we will find the ratio of the axial load on which is acting on the bearing and the radial load which is acting on the bearing. In our case, it is less than 0.7 because FA is FA upon FR is equal to 3500 divided by 6000, and this is less than 0.7. since Fa upon Fr is less than 0.7, we will go in this table. Now, in our case, since Fa upon Fr is less than 0.7, it means Fa is less than 0.7 of the Fr. It means this condition is satisfied, and so we will go for the deep groove ball bearing. Now, if it is more than 0.7, it means the thrust load component is more than the radial load component, or appreciable, not more, it is appreciable. And so, either we will go for double row ball groove bearing, you see, double row ball groove bearing, or some other bearing. So, here a single row deep groove ball bearing is suitable and it is selected. Now, based on the single row deep groove ball bearing, now we will choose tables of manufacturer where with reference to the bore, different properties of the or the parameters given in this figure are given. Like one example, this is the table from the SKF catalog, and this gives the principal dimension of the bearing, that means small d, this one, capital D, this one, and the B, this one. This D is actually the bore. So, if the bore is 17, then the type of available bearings are this one, this SKF bearing. 6 represents the deep groove ball bearing, and the diameter and width and diameter series are 00, 02, 03, 04, and the this 03, 02, 03, this one. This all represents the our bore of the bearing. So, in our case, bore is 40 mm, and so in this table there is 17, 20, 25. So, we will go in another table which is for 30 bore, 35 bore. Ours is the 40 mm, and so again we will move, and we are now at a location where the small d bore is given as 40. It means we may select this 40 and the corresponding dimensions of the bearing are this one. So, if we will select any one of it, let for example, we are selecting 6208, then the small d of the bearing will be 40, capital D outside will be 80 mm, and width means this one, this width B is 18 mm, and we will study what these two are. So, let us select SKF 6208. So, this bearing is selected. You may select any of this available bearing for the bore 40. Like in this example, for a particular type of bearings, these, the value of C, the dynamic load capacity, and C0, the static load capacity are given. So, if you have selected any particular bearing, then its dynamic load capacity will be this one in Newton, and static load capacity will be this one as per the manufacturer. This is the dynamic load rating and this one is the static load rating. Now, our bore is 40 mm. So, corresponding to this 40 mm, let us find the dynamic and static load capacity. We have selected this is the dynamic load capacity and this is the static load capacity, these columns, and we have selected 6208, and so for our case the dynamic load capacity is 30,700 Newton and static load capacity is 16,600 Newton. There are C0 is this one and C10 is this one. This is sometimes also called C10 or only only C. Now, the equivalent bearing capacity, as in our bearing both radial and axial load are acting, and so we must find the equivalent bearing capacity. The force acting on the bearing has two components, radial and thrust. Like this is the radial load and this is the thrust load, axial load, which is acting on our bearing. We have selected deep groove ball bearing, not this roller. It is therefore necessary to convert the two components acting on the bearing into a single hypothetical load fulfilling the conditions applied to the dynamic load carrying capacity. Then the hypothetical load can be compared with the dynamic load capacity of the selected bearing, and that is calculated with the equivalent load P, or it is sometimes also called Fe, is given by X V Fr. Fr is the radial component of the force which is acting on the bearing, and Fa is the axial force component which is acting on our bearing. And the V is the race rotation factor. It depends on whether the inner race is rotating or the outer race is rotating. And X and Y are determined based on this X and Y of this equation. X and Y are obtained from manufacturer's table, which is based on Fa upon C0. Fa is the axial force acting on the bearing and C0 is the static load capacity. So, this is obtained, and based on your value and based on also Fa upon Fr, axial load acting on the bearing divided by radial load acting on the bearing. If it is less than or equal to E, where E is given here. So, let us suppose Fa upon C0 for your bearing is this one, then your E will be this one. Now, Fa upon Fr is calculated and it is compared with this E. Now, if your Fa upon Fr is less than or equal to E, then X will be 1 and Y will be 0. Now, if Fa upon Fr is greater than E, then X will be this one and Y will be this one. This will be substituted in this equation to get the value of P. In our problem, the value of axial force which is acting on the bearing is 3500 Newton. It is divided by the value of C0, which is obtained by selecting the a particular bearing. We had selected a bearing and corresponding value of C0 is 16,600, and so Fa upon C0 is 0.2108. To determine the effective radial force on the bearing, we must know this Fa upon C0 and we have to find Fa upon Fr, the ratio of axial force which is acting on the bearing divided by radial force which is acting on the bearing. Therefore, we got this Fa upon C0 as 0.2108. Now, there is no any value given for our Fa upon C0, but it is lying in between the 0.113 given here and 0.25. And so, to get a value of E, we will make interpolation and we will get the E corresponding to our value of Fa upon C0, 2108. Corresponding to that, first of all we will get the value of E, and then this E will be compared with the Fa upon Fr. Fa upon Fr as per our problem is 0.5834. Okay. So, let us find first the value of E. By interpolation, we got the value of E as 0.3545. This E will be compared with the Fa upon Fr. our FA upon FR is 0.5834 and obtained E is 0.3545 and therefore, FA upon FR is greater than E. So, we will take this condition. Our FA upon FR is greater than E and therefore, the X and Y term of the effective radial force will be obtained from this column. And the X is constant, which is 0.56. So, our X will also be 0.56, but Y will be in between this 1.4 and 1.2. So, after interpolation, the Y will be obtained. So, X is 0.56 and Y is 1.252. So, the effective radial force is equal to X VFR plus Y FA. X is 0.56, V will be taken as 1 because in our case the inner race is rotating and outer race is fixed. So, for that condition V is taken as 1. Now, we will substitute the value of FR and Y is 1.258 and so we will get the effective radial force on the bearing and that is 7742 Newton. So, the load life relationship is there. So, nominally identical groups of bearings are tested to the life failure criteria at different loads. A plot of load versus life on the log-log scale is approximately linear and so we have a relationship, the force acting on it and the life to the power 1 upon A is a constant, where A is 3 for the ball bearings and A is 10.3 for the roller bearings. Now, we know that there is a relationship between the load which is acting on the bearing and the life of the bearing. Now, if two load life conditions are taken, this is on the log-log scale F and L. So, for a particular reliability, if two conditions are taken, the condition 1 and condition 2, then the relationship is F1, this is F1 and this one is L1, this is F2 and this one is L2. So, F1 L1 to the power 1 upon A is equal to F2 L2 to the power 1 upon A, denoting condition 1 with R for catalog rating condition. If this is the catalog rating condition, we know that in the case of our rolling element bearings, we do the selection design from the manufacturer's catalog. We choose a particular gear, bearing, and that bearing has a particular value of dynamic load rating and the static load rating C or C10. Now, the rated force and the rated life are FR and LR. So, FR divided by FR LR to the power 1 by A is equal to FD LD to the power 1 upon A. What we are doing is the condition 1 is taken as the rated condition as per the catalog and 2 is our design condition. This is our desired load and desired life. So, the relationship between the rated and desired is given by equation A. The life in this equation is given in number of cycles and rated life in most of the cases is 10 to the power 6 cycles. Now, in sometimes life is given in number of hours. So, if this is the life in number of hours, then the relationship between life in cycles and life in number of hours is given by L is equal to 60, this L N. N is revolution per minute. solving equation A, this one, for Fr, the rated force, which is just another notation for the catalog load rating. So, Fr will equal to Fd Lr to the power 1 upon A divided by Lr to the power 1 by A. So, Fr is equal to Fd, the desired load, within the bracket Ld divided by Lr to the power 1 upon A. Now, if the life is substituted in terms of number of hours, then this will become Ld Nd 60 divided by Lr Nr 60 to the power 1 upon A. The desired design load Fd and life Ld come from the problem statement. The rated life Lr will be stated by the specific bearing manufacturer. Many catalog rate the Lr as 10 to the power 6 revolutions. The catalog load rating C10 is used to find a suitable bearing in the catalog. It is often convenient to define a dimensionless multiple of rating life as Xd is equal to Ld divided by Lr. So, our aim is, first is to determine this 610. This is the required 610. Okay. If this required C10 is equal to or more than the C10 of the selected bearing, then it is okay. Otherwise, we will go for selecting some other bearing. Okay. The effective dynamic load as per our calculation is 7742 Newton. Now, this Fe will be substituted in this equation to get the required dynamic load of our bearing. So, this Fe is substituted here and the life in hours is given in our problem as 500 and the RPM of the bearing is 1440 RPM and the rated life in number of cycle is 10 to the power 6. So, substituting all this, we get the required value of, this is the required value of C10 as 27,165.3 Newton. Now, the bearing which was selected was SKF 6208 and for that the C10, the dynamic load rating is 30700. So, the bearing which we have selected has dynamic load as 30700 and the required dynamic load is, as per our problem, is 27165. So, this is more of our bearing and this one is lesser and so the selected bearing is suitable. And that is the example 2. A shaft is rotating at 1440 RPM, is supported by 2 bearings. The forces acting on each bearings are 6000 Newton radial and 3500 Newton axial. The shaft diameter is 40 mm, the same problem we are taking and the expected life is 500 hour, similar. But now the bearing reliability required is 99%. The rated reliability is 90%. Rated reliability of the bearings is 90% because we have said that only 10% of the bearing has failed and 90% of the bearing is safe. And so, the reliability was 90%. If we are taking C from the catalog and C0 from the catalog, then these all are based on the 90% reliability. Now, we want to design our bearing other than 90% and so let us see this problem. Let us select the bearing 6308 whose static load rating is 22,400 and the dynamic load capacity is 41,000 Newton. In this figure, on the y axis is the log of the force on the bearing, and on the x axis is the dimensionless life measure, which is L divided by L10. So, if we are at D point, then this xd is Ld divided by Lr. If we are at A point, then it will be La divided by Lr. Okay. Lr will be sometimes called L10. So, here the rated line is there as per reliability 0.90, and this is the line corresponding to our required reliability of 99%. So, this is called the design line and this is called the rated line. The design point is corresponding to the force Fd, which will be acting on our bearing, and the life is L divided by Lr or L divided by L10, and this will be called xd, the dimensionless life measure x, and A is the rated point as per the manufacturer's catalog. And so, the force will be C10, the dynamic load rating, and on the x axis it will be x10 or xa, and this xa will equal to Lr divided by Lr or L10 divided by L10, and that will be 1. This is called the x10. So, this will be a known thing A as per the rated life, and this is your design point. And so, the designer must move from point D to point A via point B, because for this particular reliability we have a relationship Fd Ld to the power 1 upon A is equal to Fb Lb to the power 1 upon A. So, D will be related to B, and force at B is equal to force at A, and therefore, from B we may come to A. Along a constant reliability contour BD, we have relationship Fb and Xb to the power 1 upon A is equal to Fd multiplied by Xd to the power 1 upon A, and so we get Fb force at B is equal to Fd within the bracket Xd divided by Xb to the power 1 upon A. Now, along a constant line AB, we have a reliability equation Rd, because here the reliability is Rd and here is the rated reliability 0.90. So, this Rd is equal to this formula. Here we will substitute the value of Xb, okay, Xb. So, Xb is obtained from this equation, which is equal to x0 plus theta minus x0 within the bracket log 1 upon Rd. Rd is the required reliability. In our problem it is 99% or 0.99. So, Xb can be obtained knowing the value of Rd and variable parameters theta x0 and b. So, we have now the xd and xb, and from this formula we have equation for Fb. So, knowing xd, xb and Fd, we will know the value of Fb. So, Fb is equal to Fd xd divided by xb. Xd is the desired non-dimensional parameter, which is equal to Ld divided by L10 or L rated Lr. So, substituting the value of Xb, we got this equation. Note that Fb is equal to C10. You see here, the force which is acting at B is equal to force acting at A, and A is the rated line or rated point. So, corresponding to this A, the force will equal to the dynamic load capacity of the bearing, which is called the C10. So, FB will equal to C10 and that will be the required dynamic load rating. So, required dynamic load rating, let me write it, this is required dynamic load rating C10 is equal to this equation. Knowing all this, you will get the required C10 as per the required reliability RD, and our required reliability is 0.99. So, when we will substitute all terms in this equation and RD equal to 0.99, we will get the required dynamic load rating. Now, suppose we have selected a particular bearing, and that bearing has some value of dynamic load capacity C10. So, the C10 of the selected bearing should be greater than or equal to the required dynamic load rating obtained from this formula. Let us see in the problem. The bore of our bearing or the shaft is 40 mm. So, corresponding to this 40 mm, we had selected 6308 bearing and the dynamic load rating of the selected bearing is 41000 Newton and the static load rating C0 is 22,400 Newton. Well, now we have to find the effective dynamic load acting on the bearing, because on our bearing both radial and axial forces are acting. And so, effective radial load or effective dynamic load Fe we have to calculate, and for Fe we have to use this table, and from this table we have to find the value of x and y, and x and y can be obtained knowing the value of E, and E is obtained by knowing the ratio Fa upon C0. So, Fa upon C0 for our case is 0.1562, which is in between these two, and so by interpolation we get the value of E as the corresponding value of E from table is 0.3308. E is somewhere here and it is 0.3308. This will be compared with the Fa upon VFR. V is 1 because inner race is rotating and outer race is fixed. So, Fa upon Fr will be obtained and it will be compared with this. So, Fa upon Fr is 0.1562 and which is lesser than this value. This is E and Fa upon C0 is 0.1562. Okay. Fa upon Fr where we have calculated Fa upon Fr is greater than E. Therefore, x is equal to 0.56. It is Fa upon R greater than, we will use this one, and this will give you the value of x, this will give you the value of y. So, after interpolation we got x as 0.56 and y as 1.35. Substituting this, we get the equivalent load Fe as 8085. This is the equivalent load. Okay. And the meaning is, this is our design line, this is our rated line. Here the force which is acting at design point is 8085. We have some value of xd and here is the rated point A, and for rated point this is C10, x10, and this will give you the value of Fa or the Fr, and that is C10 required. Okay. XD is equal to LD divided by LR, and LD is obtained knowing the life required in number of hours, and knowing the RPM, we get XD as 43.2, and the required C10, the FE we have calculated just now as 8085. This XD is obtained as 43.2, which is substituted here, and the RD is 0.99, this 0.99, and the Weibull parameters are given in our problem as theta is equal to this one, x0 as this. And so, required C10, which is also equal to, for these two curves, this is the rated curve, this is the design curve. Okay. So, this is your A point, this is your B point, and this is your C10, and that is also equal to FA and FB. So, this is the required C10 for our case with the given value of radial load, given value of the axial load, and that comes as 47,022.3 Newton. Now, let us see what is the dynamic load capacity of the bearing which we had selected. The required C10 is compared with the selected C10. The C10 of the selected bearing, we had selected SKF 6308. See here, 6308 we had selected, and its dynamic load rating is 41,000. Okay. So, 41,000 is the dynamic load rating of the selected bearing, and the required dynamic load rating is 47,022. So, required is more than the selected bearing. It means this bearing is not suitable, So, next bigger bearing is selected. What we have done is, let us see here, this we had selected, and for that case the required dynamic load is more than the dynamic load of the selected bearing, and so we will move to the next bigger one. Next bigger one is 6408, and for that the dynamic load rating is 63,700. Next bearing will be selected 6408, whose static load rating C0 is this one, and the dynamic load rating is 63,700 Newton. This one, this we had selected, and for the selected, the C10 is given by this one. Now, it has the static load rating C0 as this one. So, now again we will find FA upon C0, and from that we will get the value of E, and by comparing this E to the radial force and axial force, we will get X and Y, and this will be used to get the value of FE, and this FE will be used to get the value of C10, that is required dynamic load rating, corresponding to the required reliability RD. So, just we are going to repeat the process. Corresponding to the new value of C0, the FA upon C0 is this one, and the corresponding value of E is 0.289, 0.289. E is this one. So, it will be compared with FA upon FR, this is greater than E, and therefore, X is given by 0.56 and Y will be in between these two values, and it comes as 1.5, V is 0, and so the equivalent load now, after substituting the value of FA, FR and X and Y, comes as 8,610. So, required dynamic load rating after substituting all this is 50,110.2 Newton. The dynamic load rating of selected SKF 6408 is 63,700. So, the dynamic load rating of the selected bearing is this one, and as per our problem, the required C10 is 50,110.2, and therefore, the selected bearing has more load capacity, and hence the SKF 6408 bearing is suitable. So, in this tutorial, we took two problems. One problem was with the desired reliability equal to 90%, which is the rated reliability, and we studied the way by which bearing is selected from the manufacturer's catalog. In the another problem, the bearing was desired with reliability equal to 99%, which is other than the rated reliability. In this particular case also, we studied the way by which a suitable bearing is selected. Thank you.